So hello everyone. In this class, I'm going to discuss the working mechanism of a bipolar junction transistor and what are the current components present inside the BJT. That means what are the different current components are available. Okay. So BJT is a three-terminal device, so emitter, base, and collector. And just for this analysis, I am taking one PNP transistor. That means the emitter is a P-type, base is N-type doped, and collector is P-type doped. And you know that the main application area of BJT is to amplify the signal. And for amplification, the BJT must operate in active region. And the condition for active region, that is base emitter junction, that means we are talking about this junction. This junction should be forward biased and base collector junction should be reverse biased. Now, in this case, in this PNP transistor, the emitter is connected to some positive voltage and the base is connected to some negative voltage. Just check this voltage source, VB. So this voltage source makes this base emitter junction forward biased. Okay. Similarly, by connecting a voltage source DC in between base and collector, check the collector is P-type where we are applying a negative voltage with respect to base. So by applying a voltage VC, so this base collector junction is made reverse bias. That means now the BJT is in active region. Now let us investigate how the current will flow inside the BJT. Okay. Now when this base emitter junction, this junction is forward bias, you see, there will be diffusion of charge carrier. So why? See, the emitter is P-type doped. That means in the emitter side, the holes are the majority carriers, whereas the holes are the minority carriers in the base region because the base is N-type doped. And similarly, just opposite, in the base region, that is N-type doped region, the electrons are the majority carriers here, and the same electrons are the minority carrier in the emitter region. So since there is a concentration gradient, that means in the P side, there is a higher concentration of hole, and N side, that is the base region, there is a lower concentration of hole. So there will be some diffusion force acting on hole, and the holes will diffuse from emitter to base. Okay, and when the holes will enter into the base region, okay, they became the minority carrier because the N region majorities are electrons, so the hole became the minority carrier. So the hole will move from emitter to base region due to the diffusion process. In the same way, the majority carrier electrons, those are present in the base region, okay, they will move in the opposite direction, okay, and they came to the emitter region. Now it may be noted that in the previous lecture also I mentioned the base region, the area of a base very thin, smaller, and the doping concentration of base region is smaller compared to emitter and collector. So here only few number of majority carriers, that is electrons, are present in the base region. Okay. Now if we take a look on the current component, so when the holes are moving from emitter to base, of course there will be some current due to the movement of hole. That current, later I'm giving one name, IPE. So IPE is the whole current in the emitter side. Okay, so IPE is the whole current. E stands for emitter. Similarly, the electrons are moving from base to emitter side, so the current direction will be just opposite. Okay, so if we draw the current component, so this one will be INE. So here I can write INE is the electron current. So the total current that is due to the movement of electron and hole, and that the total current is IE in the emitter terminal. So I can write IE equals to summation of electron current plus hole current, this one. And it may be noted that since the value of electron current is very small because the base region having only few electrons, it is lightly doped and its width, its area is very small. So basically, this whole current will dominate in case of PNP transistor in between the emitter and base. Okay. So this is the situation in the emitter base region. Now the hole which are injected from emitter to base region, that means here. Now there will be some recombination in the base region. Why? Because the base region having some free electrons. The majority carriers are electrons. Okay. So some of the holes will recombine with the electrons, that is free electrons available in the base region. And due to this recombination process, some of the electron hole pairs are lost. Okay. And rest of the hole will move towards the collector region. And finally, they are collected at the collector terminal. Now see, we made this minus negative. This is connected to the negative potential. So rest of the holes will be attracted towards the collector terminal, and finally they are collected here in the collector terminal. So in the collector region, so I can write one current component ICP, so that is due to the movement of hole. Okay, the hole current in collector. So this is the value of ICP. Okay. Now check, since a few electrons are lost due to recombination in the base region, okay, and that electron will be supplied from this negative terminal of this battery, because see the VB we are applying to make this base emitter junction forward bias. The electrons which are lost, okay, those free electrons are supplied from this battery. That means the battery will supply the free electrons here into the base, and as a result, see the movement of electron from this side to this side. As a result, there will be some base current, which direction will be just opposite of the movement of electron. So the base current will flow in this direction, IB. Okay, just so basically IB is the recombination current. Base current in transistor we are getting, that is due to the recombination in the base region, and rest of the hole will reach at the collector terminal, and finally we are getting the collector terminal. So if we write the relation between this collector current and emitter current here, so let's, for example, if 100 number of holes are entering from emitter to base region, and out of 100, 5 holes are lost due to recombination, the rest, that is 95 holes, are finally reached at the collector side. So the current ICP we are getting, that is due to those 95 number of holes. So mathematically I can write, okay, so ICP, so that is due to that 95 number of holes, for example, that is a fraction of emitter current alpha times of IE. And alpha, of course, it is less than 1 because we lost some hole due to the recombination in the base region. Okay. So ICP, that is equal to alpha times of IE. So alpha is a parameter. So later we shall discuss what is alpha, how we can define alpha, and all these things. Now, let's analyze some other things, other current components. Those are present inside this BJT. Till now, we analyzed the current component, which are coming from the emitter side, and we analyzed the recombination process that is in the base region, and we got some current in the collector side. Apart from that, there will be some leakage current in this transistor because the base collector junction is reverse biased. And from our previous discussion, we know that when a PN junction is reverse biased, there will be some small value of current that is basically due to thermally generated carriers. Due to temperature effect, some of the covalent bonds are broken, so few electron hole pairs are available inside the structure, and due to applied bias voltage, those free electrons and holes will move according to the polarity of the voltage we are applying, and as a result, a very small amount of current will flow in the circuit. That is basically the reverse current, or we can say that leakage current of the device. So let's investigate the transistor. What will be the value of those leakage current? Now see one thing, the base collector junction is made reverse bias, this one. So we are going to analyze the leakage current component that is in between the base and collector region. Let's To analyze the leakage current, the first thing is that since we are focusing on the base collector junction, so we are not paying attention to the emitter base junction. So emitter region, base region, collector region. That means the emitter base junction, the voltage we are applying here, okay, so that now in this case it is open because we are interested to find out the current component between the base and collector junction here. So this one is our N region, P region, and P region, PNP transistor. Okay. And this junction is reverse bias, that means this. This. Now, due to temperature effect, let some electron hole pairs are available here. Okay. Some free electrons and holes are available. So of course, the holes will move towards the negative potential. The holes will move towards this potential because here we apply that negative voltage and the electrons will move towards this side. That means the movement of electron will be towards this. So as a result, we are getting some current due to the movement of this thermally generated electron and hole, and the direction of current will be from this towards this because the hole will move in this direction and the electrons are moving from this side to this side. As a result, the current due to electron, you will get just opposite. So the current will flow from base to collector for PNP transistor and it's just opposite for NPN transistor. Okay. So this current we are giving one name ICO. Okay. So ICO is the leakage current in the structure when the collector base junction is reverse bias. So it is having two components, ICO of N plus ICO of P. So ICO of N, that is the contribution due to the electron, and ICO P, that is the contribution of leakage current due to the hole. Okay, this is. Now adding all the components. So in a previous diagram, we have seen that we have one current component that is coming from emitter and base, that is ICP. Okay. So this current, let's draw here. This current is ICP. And we have another one current component ICO. So if I mention this one is collector current IC, and if I apply KCL at this point, or simply you can write that the collector current will be summation of this ICP and ICO. So basically this part, second part is the leakage current component, and first part is the current which we are getting due to the holes which finally collected in the collector terminal after recombination. Now previously I already mentioned this. I can write this in form of alpha times of IE. So IC that is equal to ICP, that is alpha times of IE plus ICO. So basically this is the relation between the collector current and emitter current and also the leakage current. So this is the current equation of BJT. And another one interesting thing you can check. So this is our collector current IC. Now if you take a look on the collector, emitter and base terminal, and if I apply KCL, see the incoming current is IE and the outgoing part is base current IB and collector current IC. So emitter current is equal to base current plus collector current. This is the relation between the three terminal currents of a BJT. The emitter current is nothing but summation of base current and collector current. Okay. With the base current is due to recombination, we lost a few holes due to recombination, and rest of the holes finally are collected in the collector terminal. So of course, the current IE will be equal to IC plus IB. So I think it's clear. Now we can further simplify this one. So now using the equation, so we have IC equals to alpha IE plus of ICO, and we have the relation between different current component IE equal to IC plus IB. Now from this equation I can write IC equal to IE here. I can replace IE by using this IC plus IB. I'm going to put the value of IE here. That is alpha times of IC plus IB plus ICO. And if I take IC common, 1 minus alpha, that is alpha times of IB plus ICO. So the relation we got IC equal to alpha by 1 minus alpha into IB plus ICO by 1 minus alpha. Now the factor alpha by 1 minus alpha is represented by using another one constant that is called beta. So then this 1 by 1 minus alpha, so here this part, so 1 by 1 minus alpha will be beta plus 1. So the final current expression we got in a different form, IC equals to beta IB plus beta plus 1 ICO. So this is another one current expression in a different form. So this is one equation, and after replacing all those values, we got this is another one equation. Now from this equation, we can write, just see, since the value of leakage current is small compared to other part, so neglecting the ICO here, we can just write alpha equals to IC by IE. And here in this equation, the beta equals to IC by IB, neglecting leakage current ICO. So basically alpha and beta both are ratio of two currents, so they are basically current gain. The alpha and beta, they are current gain. Now let us see how we can define the alpha and beta and what will be the typical value for alpha and beta. So alpha equal to IC by IE. Now, if we take a look on the common base mode, so the base is common, emitter is the input, collector is the output. So just take. Now here, the alpha equal to IC by IE, and this is the common base mode of BJT. The base is common between the emitter and collector configuration. So of course, the emitter is the input current and collector current is the output current. So IC by IE, so that define the common base mode current gain, and the value of alpha is less than 1 because the emitter current value is always greater than the collector current value, and the typical range of alpha is generally 0.95 to 0.99 for a BJT. Similarly, beta equal to IC by IB. And of course, the value of IB is very small, generally in microampere range compared to IC. So beta is greater than 1, and generally the typical value of beta for a BJT is within 50 to 200 in that range. And how we can define beta, just take in the common emitter mode. So this is the C mode of BJT, common emitter, where emitter is common in between base and collector. IB is the input current, IC is the output current. So IC by IB that define the common emitter mode current gain. And another one parameter we may introduce that is called gamma. So gamma is the emitter current by base current, IE by IB. So gamma is called emitter injection efficiency. Emitter injection efficiency. And also you can correlate gamma with alpha and beta. So gamma equal to beta plus 1. And you can also represented in this form is beta by alpha, because beta equal to IC by IB, alpha equal to IC by IE. So this term and this term will be cancelled. So it will be IE by IB. So that is nothing but gamma. So those are the different current gains for BJT, alpha, beta, and gamma, and their relation. And another one thing, see the ICO, that is the leakage current. In some textbook, it is mentioned as ICBO. So it is the leakage current. The CBO, BO stands for base is open. That means we are analyzing the leakage current when the base emitter, the voltage between the base emitter, so this terminal is open basically. We are not applying any voltage here. And only the base collector junction is reverse bias. In that condition, we are getting the leakage current, so that is ICO or ICBO. So this is all about the working mechanism of and current components of the BJT and their relation. So thank you. In the next class, we shall discuss that characteristics of BJT in different mode, that is input characteristics and output characteristics for common emitter and common base mode.